Welcome back everyone. In this lecture we will be continuing with the study of highest weight representations. So let us fix V being finite dimensional highest weight representation with generated by V small v, which is a highest weight vector with highest weight lambda. Okay. So, note that means HV is given by lambda of HV for all H in H and XV is 0 for all X in N plus. So, we actually defined the Casimir operator and then we saw that the Casimir operator acts as some scalar times on V, and this Casimir operator, the scalar is given very explicitly in terms of in terms of the lambda. So, recall, so this is given by summation di square I range from 1 to n plus summation di minus dj I less than j less than or equal to n plus 1 greater than or equal to 1. So, where we take this h lambda to be this d1 so d1 e11 plus etcetera plus d n plus 1 e n plus 1 e n plus 1 n plus 1. So, we have this very explicit formula for the scalar. So, and we can actually simplify this scalar. So, I will leave that as exercise. So, if you take the C lambda, then you can simplify the second sum as summation dA square and then plus summation. Okay. So, if you think about it, actually like you do not need this summation. So, you can just simply run it over I range from 1 to n, because you can collect all the coefficients of dI, and then if you collect it, you can easily see that this is n plus 2 minus 2I times dI. Okay. So, this is the formula that you get it for C lambda. So, this is very explicit in terms of lambda. So, now we are going to actually use this explicit formula in order to actually conclude something more about the C lambdas. So, here is the proportion. So, this is somewhat very powerful observation in some sense. So, if you take this C lambda, now C lambda is defined for any lambda, okay, because H is identified with H star. So, you take any dominant weight lambda, you will be able to define C lambda. So, now for any lambda dominant, okay, so we can conclude that this C lambda must be always non-negative, and we have the equality C lambda is 0 if and only if lambda being 0. So, this is somewhat very important thing, and if lambda mu both are dominant and mu is smaller than lambda with respect to the dominance order. So, then one can conclude that C lambda must be greater than or equal to C mu, and in this case the equality happens. So, in this case the equality happens if and only if lambda equal to mu. Okay. If mu less than or equal to lambda and C lambda equal to C mu, that implies lambda equal to mu, that is what it means. So, what that is, mu less than or equal to lambda, of course, lambda mu both given to be dominant, and C lambda equal to C mu, this implies lambda equal to mu. So, this is something very important observation. So, let us actually do one by one. So, since we have written everything in terms of the standard basis, so we have to actually translate everything to that. So, recall So, lambda of hi being non-negative integer, that is same as the definition of lambda being dominant for I range from 1 to n. Now, this is same as saying that so if you write this h lambda in terms of the standard basis, so then this lambda of hi you can actually easily conclude, because this is being b of h lambda hi and hi being ei minus ejj. So, this is exactly given by di minus di plus 1, and which is non-negative integer. Okay. So, this is just translates to di minus di plus 1 being non-negative integer. So, now if you actually look at the formula, okay, so this means what? This means, so this is true for each I range from 1 to n. So, now this means d 1 must be greater than or equal to d 2, greater than or equal to etcetera, greater than or equal to d n plus 1. So, that is the meaning of this lambda of hi is being dominant weight. Okay. So, there is actually somewhat slight difference between considering GLN representations as well and SLN representations. Okay. So, this change of basis always actually matters a lot. Okay. But the only thing that matters, so we have to consider finite dimensional integral representations of GLN if you are interested in actually pushing down to the SLN. Okay. So, because the integrality is actually always there, so we always assume that the coefficients that we are getting, okay, so those are all like integers. So, we are going to work with only the integral combination of epsilon i's, nothing more. So, that is what I mean. Okay. So, we take this z plus span of epsilon 1 etcetera epsilon n plus 1, and this is where we are working. So, this is where we are doing the computation. We are doing the computation. But anyway, like here, so this is something like nothing to do with so when we consider GLN representation, I will explain what I mean by these translations. Okay. So, now lambda being just dominant just says that lambda hi is being non-negative integer. So, that just translates this di is being decreasing. Okay. But the thing is, the only thing that we have actually encoded, that the difference di minus di plus 1 is always non-negative integer. So, we are not saying anything about di's being integers. Okay. But in practice, whenever we want to consider SLN representation, it is okay to consider like all the di's are integers. So, that will be equivalent to considering like either d1 is integer or dn plus 1 is integer. So, that demand is always there. Okay. But here we do not need to worry. So, these computations nothing like it is not going to affect anything. So, we have this constraint. So, now if you go back to your equation, you can easily see that. So, this equation actually has something like this. So, these terms are already non-negative. So, di squares are already non-negative. As long as okay, di's are actually real numbers, then we are in business. Okay. So, we do not need to. So, for example, like we can just simply take dn plus 1 to be 0 to begin with. So, when you actually do the translation from the standard basis to actually the SLN basis. Okay. So, what I mean by standard basis, the standard basis is E11 etc. ENN, but from this we have to go to E11 minus E22 etc. ENN minus EN plus 1 n plus 1. So, that translation is what we are talking about. So, let us make everything precise. So, let us observe something about this h lambda. So, lambda is coming from the dominant weight. So, that means all we know is lambda of hi is being non-negative integers. Okay. So, this is what is encoded in this information, but to begin with lambda plus is contained in lambda. So, lambda hi is all of them are integers, that is already there. So, if I take lambda, if I write it in terms of the like either alpha i's or omega i's. So, let us write it in the omega i's basis, then this is given by summation lambda of hi omega I, where I range from 1 to n. So, this is what lambda, and this is well defined element in h star, because h star is nothing but span of alpha 1 etc. alpha n. So, where alpha I is given by epsilon I minus epsilon I plus 1, indeed the bar. Okay. So, let us start putting the bar. So, now what is h lambda? H lambda is defined to be B of h lambda of h is given by lambda of h. So, in particularly B of h lambda hi is given to be lambda of hi. So, this is how h lambda is defined. Now, if you take h lambda and then if you write it in terms of the usual basis of h, okay, so that is indeed you are writing, let us say some scalars, let us say a1 h1 plus etc. plus a n h n. So, then from this you can actually see like what will be AIs. So, B of h lambda hi, okay. So, maybe we can actually write it in terms of hi star basis. Yeah, maybe we will write it like, so we should write it in the hi star basis. So, then it is easy to see that B of h lambda hi is given by the AI. So, now this is nothing but lambda of hi. Okay. So, this is the AI that is coming in when you write it in terms of omega I. So, this is the AI that you are getting, and these are all non-negative integers. Okay. Since this hi to hi star, okay, maybe you can actually work it out very explicitly. The change of basis, so that is going to be over integers. So, because of that, so if you rewrite this h lambda in terms of h i's, okay, let us say summation some b I h I, we can conclude that this b i's must be rational. So, that is for sure. So, this must be rationals. Okay. So, I will leave it as exercise. The change of basis or the transition matrix, okay, the transition matrix from the basis Hi to Hj star is defined over rationals. So, that is good enough for us, okay, and it is invertible matrix. So, if you rewrite in terms of the other basis, so you are going to actually get coefficients from Q. But now, if these BIs are coming from Q, then what will happen to these DIs? These DIs also will come from Q, okay. At least for sure we can assume that these are all coming from Q. So, that is why we can easily see these numbers are non-negative real numbers. So, now these relations actually tells you that D1 is greater than or equal to etcetera Dn plus 1. Okay. So, since D1 is greater than or equal to Dn plus 1, now if you compute Di minus Dj for I less than j, you can see that this is nothing but Di minus Di plus 1 plus Di plus 1 minus Di plus 2 plus etcetera plus Dj minus Dj minus 1 minus Dj. And since all these numbers are in the decreasing order, so you can see that this is all greater than or equal to 0. So, this tells you that this C lambda is at least summation Ti square, which is greater than or equal to 0. So, whenever lambda dominant, so we can see that C lambda must be non-negative. And now, from this calculation, you can easily see that C lambda is 0 if and only if the summation Di square is 0, Di being rational, that means if and only if Di is 0 for each I, and that means lambda is 0. Okay. So, this just means lambda 0. So, now we will again use similar observation and then prove this second statement. The second statement says whenever lambda mu both are dominant, so you know that both C lambda C mu they are all non-negative integers, but you can conclude that C lambda must be bigger than C mu, and the equality happens only if lambda equal to mu. So, that is again like comes from the explicit formula. So, maybe I will actually just indicate what one needs to prove and then I will leave it as exercise. So, here is the exercise. So, if you compute this C lambda minus C mu, so you take this gamma I to be these numbers, the difference between these numbers. So, let us write it as D1 lambda plus etcetera plus Di lambda minus D1 mu plus etcetera plus Di mu. So, where what is D1 lambda? So, lambda, so H lambda you are writing it as summation Di lambda Ei, where I range from 1 to n plus 1. So, then if you use this notation, then C lambda minus C mu is nothing but summation gamma I range from 1 to n times C I minus C I plus 1 plus D I lambda D I plus 1 lambda plus D I mu minus D I plus 1 mu plus 2. So, this is what you get. So, we already know that lambda being dominant, Di is greater than or equal to Di plus 1. So, this term is greater than or equal to 0 and this term is greater than or equal to 0, that is being lambda being dominant and mu being dominant. Now, since lambda greater than or equal to mu, if you write it in the epsilon I basis, that translates to actually this gamma I being greater than or equal to 0. Okay. So, this translates to gamma I being greater than or equal to 0. So, this is something I will leave it as exercise. So, then you can easily conclude that C lambda is greater than or equal to C mu. And now, C lambda equal to C mu. So, that implies you can easily see that. So, this gamma i's must be 0, there is no other option. So, gamma i's must be 0 for all I, and this would imply that, so these terms all of them are same. So, that means lambda equal to mu. Okay. So, maybe this contains 3 exercise. So, this is 1, this is 2 and this is 3. So, these are also just simple computations, so that you will be able to comfortably do, and this actually tells you that whenever C lambda equal to C mu, then we get lambda equal to mu, and C lambda is always greater than or equal to C mu if lambda mu are both dominant and lambda is greater than or equal to mu with respect to the dominance order. So, this is all simple translations. So, using this we can prove our theorem. So, our theorem actually says, so V is a, let us say, 5 dimensional representation. So, then V is a highest weight representation if and only if V is irreducible. So, we already proved this other way. So, because V is being finite dimensional, so we must have a highest weight vector. So, once you pick non-zero highest weight vector, then if you generate module generated by that vector, that must be exactly V if V is irreducible. So, that will force that V being highest weight representation. So, now we will prove the converse. So, conversely, assume that V is a highest weight representation. Of course, finite dimensional is also there. So, then we know that CV acts as identity on V up to a scalar that is given by C lambda. So, this is already there. So, now if you choose V dash as before being irreducible submodule. So, this is G submodule of smallest dimension. So, that means that forces this is irreducible. So, then you can easily see that CV restricted to V dash is going to be again C lambda identity on V dash. But we already know using Schur's lemma. So, this must act as a scalar, then scalar, because this is again being this V irreducible implies highest weight representation of, let us say, some highest weight mu, then this has to be C mu identity on V dash. So, now this lambda is already highest weight for capital V, and mu is being weight for capital V, that will force that mu must be less than or equal to lambda. So, this is there, and C mu must be equal to C lambda with this equality. So, now lambda comes from highest weight of this capital V. So, this must be dominant, and mu is the highest weight of this V dash, that is highest weight representation. So, that also must be dominant. So, all these things we gave it for free. So, that should imply that lambda equal to mu. But we already know that this dimension of V lambda must be one dimensional, because this is just spanned by this CV. So, that says this highest weight vector that spans this V dash. So, let's actually call it UG V dash that generates V dash. So, this V dash must lie inside this one dimensional space CV, because they have same weight and the weight space is one dimensional. So, that forces that this V dash is equal to V, because V dash and V, they are multiple of each other. Obviously, V dash will be both non-zero, so thus multiple must be non-zero scalar. So, that forces that V dash is indeed equal to V. So, this proves that any finite dimensional representation, highest rate representation must be irreducible. So, this is indeed very nice proof using the Casimir operator. So, now if we actually go back to our actually the climb that we made, okay. So, let us make it as a theorem. So, what happens like, so we still have not proved that the existence of either the highest weight representation or irreducible representation that corresponds to the weight lambda, okay. Let us say lambda is given dominant. But what is about the uniqueness? Okay, there are two things that is coming up very naturally. So, the uniqueness is easy to prove. Okay, let V and W be two highest weight representations corresponding to the highest weight lambda. Okay, so, we are fixing lambda, which is must be dominant, because we assume everything is finite dimensional. So, then we are saying that let us say there are two highest weight representations. So, then we prove that V must be isomorphic to W. So, that means up to isomorphism there can be at most one highest weight representation that corresponds to the weight lambda. So, this theorem actually allows us to focus on the existence. So, what is the proof? This is again very clever proof. Look at V direct sum W. So, call this V to be the generator of capital V of weight lambda, call W to be the generator of W of weight lambda. Then it is easy to see that this VW, so this is going to be highest weight vector of weight lambda. So, by definition of highest weight, we know that HV is lambda HV and then XV is 0. Similarly, HW is lambda of HW and XW is 0, and this is true for all X in N plus, and this is true for all H in H. So, now using these equations, you can easily conclude that this HVW must be lambda of HVW and XVW must be 0. So, that means this is highest weight vector. So, now take the module U, which is generated by this highest weight vector, then we know that it must be irreducible representation from our previous theorem. So, now we have the following projections. Take this projection on V from V direct sum W to V, and similarly we have this projection on W. So, this is the projection on V and this is the projection on W. So, projection on the first coordinate and projection on the second coordinate, and projections are G module maps, that is easy to see. So, what we are going to do? We are going to actually restrict these projections to U. So, you have the map from U to V, which is given by pi V restricted to U. Similarly, you have a map from U to W, which is given by pi W restricted to U. Note that the highest vector V comma W, that will be mapped to V here, and then this will be mapped to W here, and both of them are non-zeros. So, that means both the maps are non-zero maps. Now, using Schur's lemma, you can see that all the modules that are involved in this picture, all of them are irreducible modules. So, that forces that, so both these maps, they are isomorphs. So, that implies that W must be isomorphic to V. Okay. So, this actually tells, so given lambda, which is dominant, there is at most one irreducible representation corresponding to lambda. Okay, so we will actually having proved the existence. So we will actually get to the existence in the next class. So I will stop here. Thank you.